Imagine walking into a massive, just sprawling, perfectly automated factory.
Oh, yeah. Like one of those giant car manufacturing plants.
Exactly, yeah.
Yeah.
You have robotic arms spinning around, conveyor belts crisscrossing overhead, alarms occasionally flashing. And, if you just stand there, it looks like absolute chaos.
Complete bedlam.
Right. But if you actually trace the lines of production, you realize that every single movement is totally orchestrated. Like, nothing happens without a reason, and everything reacts to a specific event.
Mm-hmm.
And, well, that orchestrated chaos is exactly what AWS serverless architecture does, like millions of times a second. So welcome to today's deep dive.
Glad to be here.
Yeah. And whether you are, actively cramming for the AWS SaaCO3 exam, or maybe you're just trying to understand how these massive cloud applications manage to stay online during like a Super Bowl ad spike.
Which is no small feat, by the way.
Definitely not. Well, we are relying on a really fantastic source document today for you. It's titled The Event Machine, Mastering AWS Serverless Architecture. And our mission is to break down the exact components you need to know to build this factory, specifically Lambda, SQS, SNS, and EventBridge.
Yeah, and it really requires a fundamental shift in your mindset because mastering these tools, it isn't just about memorizing acronyms for some multiple choice test.
Right.
It's really about understanding the structural philosophy of decoupled, resilient architecture. You have to grasp the why behind systems that can scale up to handle millions of users and then, scale right back down to zero without costing you an absolute fortune.
Okay, let's unpack this, because before we can even look at how the conveyor belts move messages around in our metaphorical factory, we first need to look at the machines that are actually doing the work.
The heavy lifters.
Exactly, the core engine of this entire serverless setup. And according to our source material, that engine is AWS Lambda.
Yeah, AWS Lambda.
And the text zeroes in on two key properties that you absolutely have to understand, which are triggers and concurrency limits.
Right, so Lambda is basically compute power on demand. You aren't provisioning a server that just sits there running 24/7, chewing through your budget while it literally just waits for something to do.
Yeah, spinning its wheels.
Exactly. You just provide the code, the specific task you want done. But that code, well, it requires a stimulus to run.
So if I'm translating this into real-world terms, a Lambda trigger sounds a lot like a motion sensor security light on a driveway.
Oh, that's a great way to put it.
Yeah. Because the light bulb doesn't stay on all night. It just sits completely dark, doing nothing, costing nothing, until a very specific event happens. Someone walks past the sensor, the motion's detected, and then boom, the light snaps on to do its job.
What's fascinating here is how that analogy really mirrors the ephemeral nature of serverless computing. Once the movement stops, the light turns back off. In an AWS environment, the trigger replacing that motion sensor could be, well, almost anything.
Like what?
It might be a new image file being uploaded to an S3 storage bucket, or it might be a row changing in a database somewhere, or it could even be an HTTP request coming in from a user who just clicked a Buy Now button on a website.
Oh, okay.
Yeah, and the moment that event occurs, Lambda spins up a microcontainer, which is essentially this tiny, isolated computing environment that's just big enough to hold your code. It runs the task and then immediately shuts down and destroys that container.
Wow. The efficiency of that is incredibly elegant.
It really is.
But I'm going to push back on the second property the text highlights, which is concurrency limits, because everything you read about serverless architecture heavily promotes infinite scalability.
Oh, yeah. That's the huge marketing pitch.
Right. That is the primary selling point. If one person walks up the driveway, you get one light. If 100,000 people walk up, you instantly get 100,000 lights.
In theory, yes.
So if serverless is supposed to be this magically infinite resource, why does AWS impose concurrency limits? Is it just like a financial safety net to keep us from accidentally blowing the metaphorical fuse and bankrupting our accounts?
Well, while those financial guardrails definitely exist, the concurrency limit is actually a structural necessity.
Really?
Yeah. Your Lambda function might be able to scale infinitely and instantaneously, but you have to consider what your Lambda function is actually talking to.
Oh, like the other parts of the system.
Exactly. It rarely works in total isolation. It usually has to, retrieve data from a relational database, or maybe send a payload to a legacy on-premise server, or interact with some third-party payment API.
Right, and those aren't serverless.
Exactly. Those downstream systems are usually not serverless. They are traditional servers with very real, very hard physical limits on CPU, memory, and connection pools.
Oh, I see. So the concurrency limit isn't a flaw in Lambda's design at all. It's a structural blast shield for the legacy systems living downstream.
That's a perfect term for it. A blast shield.
Because if Lambda scales to, I don't know, 10,000 concurrent executions in a single millisecond, and then 10,000 functions try to open a connection to an older relational database simultaneously, you don't just blow a financial fuse, you completely crush the database.
You take it entirely offline. Without that blast shield, a minor traffic spike basically turns into a denial of service attack on your own infrastructure.
Wow.
Yeah, and understanding that constraint is really the critical first step in realizing why we can't just wire everything directly to Lambda. If every component is hardwired to an engine that can accelerate that violently, well, the whole machine just shakes itself apart under pressure.
Here's where it gets really interesting, because that vulnerability is exactly what the rest of our source material tries to solve.
Yes, the decoupling phase.
Right, because if Lambda can easily overwhelm the rest of our system, we need a way to manage the flow of data and, smooth out those spikes. This introduces the core architectural philosophy that the text insists you need for the SAA CO3 exam, which is building decoupled event-driven architectures.
A very popular buzzword right now.
Totally. And we're looking at 3 specific intermediary services here: SQS, SNS, and EventBridge. And I want to test a vertical mailroom analogy to see if we can decode the technical differences between these 3.
All right, let's see how the mailroom holds up.
Okay, so if I am imagining SQS, which is Simple Queue Service, I'm picturing a strict single-file line in that mailroom.
Okay.
Letters come in from the outside world, they get placed onto a conveyor belt in an orderly line, and the mail clerks, our Lambda functions, take the next letter off the front of the belt whenever they're ready. So it's basically a buffer.
Spot on. That's a queue.
Now, SNS Simple Notification Service is described as a fan-out. So instead of a patient line, I'm picturing a clerk with a massive broadcast megaphone. One message comes in, and the clerk just yells it out to the entire building. Every system listening gets a copy of that exact same message instantly.
Yep. The structural foundation of that mailroom analogy is totally solid. SQS handles the backlog to prevent systems from being overwhelmed, and SNS handles high-throughput, instantaneous mass broadcast.
Okay, but then there's the third service, EventBridge, which is labeled an event bus. And I gotta be honest, I struggle to see how an event bus is functionally different from the megaphone. Aren't we just inventing new corporate buzzwords for moving messages around?
It definitely sounds like it at first glance, but if we connect this to the bigger picture, EventBridge is where the actual intelligence of the system lives.
Intelligence.
Yeah. To stretch your analogy a bit, EventBridge isn't just someone yelling with a megaphone. It is a highly meticulous routing director who actually opens and reads the contents of the envelope, checks a master list of really complex corporate rules, and then decides exactly who needs to see this specific piece of mail.
Wait, but doesn't SNS have message filtering? I thought the megaphone could, choose who it yells at.
It can, and honestly, that is a crucial nuance for the exam.
Okay.
SNS does have a message filtering feature. It can look at basic attributes attached to the outside of the message and drop it before sending it to a specific subscriber. But EventBridge operates on a totally different level of complexity.
Oh, so?
EventBridge can inspect deeply nested JSON payloads, it looks way inside the data. It features a schema registry to validate the structure of the events. And perhaps most importantly for enterprise architectures, it is built to easily route events across dozens of different AWS accounts and even integrate directly with third-party SaaS applications.
Oh, wow.
Yeah, so SNS is high-throughput PubSub. EventBridge is a centralized, highly intelligent routing hub for the entire organization.
Got it. So by decoupling the architecture with these tools, we ensure that if a massive, say, Black Friday spike hits, the front-end website doesn't crash.
Exactly.
The orders just stack up safely in the SQS queue, or they get routed appropriately by EventBridge, and they just patiently wait for the downstream billing and shipping services to catch up.
It acts as a massive shock absorber. You're trading a slight delay in processing time for absolute architectural resilience.
Right. But, buffering only works if the downstream system eventually recovers and can actually process the data.
That's the catch.
Yeah, because if we are building these massive, complex event machines, things are inevitably going to break.
Great.
Network timeouts happen. Third-party APIs go down. Developers deploy buggy code.
All the time.
Right. So what does this all mean when a message in this perfectly decoupled system fails to process?
Well, that introduces the concept of dead letter queues, or DLQs,
Yeah.
because in distributed systems, failure is just an inevitability. You have to design the architecture assuming that lambdas will crash and databases will experience micro outages.
Okay, so in a real-world postal service, the dead letter office is where mail goes when the address is just completely illegible. It's literally a room full of undeliverable mail.
Yes.
But applying that to cloud architecture feels a bit like, I don't know, sweeping errors under the rug. Does tossing failing application messages into a dead letter queue actually solve the root problem?
This raises an important question about operational excellence, actually,
Yeah.
because a DLQ is the exact opposite of sweeping errors under the rug.
Oh, really?
Yeah. It is a triage mechanism designed specifically to protect the healthy pace of the system. Let's say you have an SQS queue processing thousands of perfectly formatted transaction records, and somehow just one corrupted record gets uploaded.
Okay.
A Lambda function pulls that corrupted record off the queue, tries to parse it, and then throws a fatal exception.
Meaning the Lambda crashes. But SQS is built for durability, right? So it doesn't just delete a message because a consumer crashed.
Precisely. SQS uses a mechanism called a visibility timeout. When Lambda pulls the message, SQS just hides it temporarily from other consumers. But since the Lambda crashed and never explicitly told SQS, hey, I successfully processed this, you can delete it, that visibility timeout eventually expires. SQS just assumes the Lambda had a transient network glitch, so it makes the message visible on the queue again.
And then another Lambda function grabs that exact same corrupted record, crashes again, and the cycle repeats. SQS is basically going to feed it that same bad data forever.
Exactly. This is known in the industry as a poison pill message.
A poison pill. Yikes.
Yeah, because it just sits at the front of your queue, endlessly crashing your compute resources. It blocks all the thousands of healthy, normal messages lined up behind it. Your entire processing pipeline grinds to a complete halt because of one single bad payload.
So the dead letter queue is essentially the circuit breaker for the poison pill. We configure the main queue with a rule that says, hey, if this specific message fails to process 3 times, stop trying. Pull it out of the main line and drop it into the DLQ.
You got it. And by isolating that failure, the main queue is instantly unblocked. The healthy messages start flowing again, the event machine keeps humming, and your engineering team receives an automated alert from the DLQ.
Oh, so they can go look at it.
Right, they can manually inspect that corrupted payload to figure out why it crashed the parser, and they can do so without the massive pressure of the entire application being down. It isolates the bleeding.
That makes total sense. All right, we have the core components mapped out now. We understand Lambda's triggers and its blast shield concurrency limits. We see SQS as the patient buffer, SNS as the mass megaphone, and EventBridge as the intelligent cross-account router.
Yep.
And we have dead letter queues triaging the poison pills. Now we need to look at how this materializes on the SAA-CO3 exam, because our source material stresses that the test doesn't just ask for basic definitions, it demands architectural application.
The exam presents these very specific scenarios where a system is failing, and you have to identify the correct AWS service to fix it. You really have to decode the specific language AWS uses in the prompts.
Okay, let's start with a classic phrase the source highlights, which is process messages reliably at scale. The text hints that reliably is a secret code word here.
It absolutely is.
But aren't SNS and SQS both highly reliable, fully managed AWS services? Why does the exam treat reliable as a neon sign pointing directly to SQS?
Because it comes down to the architectural difference between availability and durability.
Okay, break that down for me.
So, SNS is highly available. The service itself rarely, if ever, goes down. But its nature is fire and forget. When SNS broadcasts a message, if the recipient service happens to be offline, or maybe it's just scaling up or it's overwhelmed at that exact millisecond, that recipient misses the message.
And it's just gone.
It is gone forever. SNS does not hold on to it.
Oh, wow. Whereas SQS is built for durability. The message goes into the queue and is physically stored on disk across multiple availability zones.
Right.
It stays there until the consumer explicitly deletes it. If the consumer is offline for 3 hours, the message just waits patiently.
Yes. That guarantee of no data loss is exactly what AWS means by reliably processing messages. If an exam prompt mentions dropped orders, lost transactions, or the need to ensure every single message is processed eventually, they are testing your knowledge of SQS.
Okay, that is a massive tip. Now, the source material also provides an audio description of a worked architecture diagram, plus 3 practice exam questions to test these concepts. Let's walk through that diagram first so we can, visualize the board. We start with a client application sending an HTTP request. That request hits API gateway.
An API gateway is the managed front door. It handles the incoming web traffic, manages the API endpoints, and deals with authorization. But it doesn't do the heavy lifting of processing the business logic.
Instead, API gateway immediately hands that incoming payload off to an SQS queue. So we are buffering the incoming traffic the exact second it enters the AWS environment, so we don't drop anything during a sudden spike.
Beautiful design. And from there, the Lambda function is configured to pull that SQS queue.
Right.
It grabs a batch of messages, executes the code, perhaps validating an order, and writes the resulting data to DynamoDB, which is AWS's fully managed, highly scalable NoSQL database.
And if the Lambda function crashes while trying to process a bad order format, the message returns to SQS, hits the retry limit, and drops into the attached DLQ. So it's API gateway to SQS, SQS to Lambda, Lambda to DynamoDB, with the DLQ catching the fallout.
That flow is the absolute gold standard for serverless ingestion. Let's see how the source material tests that architecture with its practice questions.
Okay, question 1 from the text. A company has a decoupled application where a front-end web tier sends orders to a back-end processing tier. During peak hours, the back-end tier cannot keep up with the volume, and customer orders are being dropped. What is the most reliable way to decouple these tiers to ensure no orders are lost?
Okay, this is a textbook example of the terminology we just discussed.
Yeah, right away, the phrase "cannot keep up with the volume" tells me we have a concurrency or compute bottleneck. And ensure no orders are lost just screams durability.
Exactly.
So if I look at the distractors, one of the options is to put an SNS topic between the tiers. But based on our breakdown, SNS would just yell the orders at a back-end tier that is already grounding. It doesn't solve the dropped order problem at all.
Placing SQS between the tiers is the only correct answer there. The front-end tier drops the orders into the queue instantly, which gives the customer a really fast response time. Then the back-end tier pulls from the queue at its own maximum pace.
The queue absorbs the peak traffic. Let's move to question 2. A global architecture needs to evaluate incoming JSON event payloads originating from dozens of different AWS accounts. The routing logic requires analyzing deeply nested fields within the JSON structure to determine which specific downstream service should process it. Which service should you choose?
The exam writers are basically testing your ability to differentiate between the megaphone and the intelligent router here.
Yeah, because a lot of test takers might see routing logic and JSON payloads and immediately think of SNS message filtering. We know SNS can filter messages.
They do, and it's a common trap.
But the prompt specifically mentions dozens of different AWS accounts and deeply nested fields. And SNS filtering is, well, relatively flat. It looks at message attributes on the outside, not deeply inside the complex JSON body itself. Furthermore, managing cross-account routing at scale with SNS becomes an administrative nightmare.
You're right on the money. EventBridge is the designated answer here. EventBridge buses are natively designed to ingest events from other AWS accounts. And furthermore, its rule engine allows you to write complex content-based routing patterns that actually evaluate the deeply nested data inside the JSON payload itself.
Wow.
It is purpose-built for this exact enterprise scenario.
Excellent. Finally, let's hit question 3. A Lambda function is processing records from an SQS queue. Occasionally, an incorrectly formatted record causes the Lambda function to throw a fatal exception. The function continually retries this same record, preventing other valid records from being processed. How should a solutions architect resolve this issue?
The classic poison pill scenario. And notice how the exam frames the symptom preventing other valid records from being processed.
Yeah. And one of the distractor answers here is usually increase the Lambda concurrency limit. But we know that doesn't solve a corrupted file. It just spins up more Lambdas to crash on the exact same file. Another distractor might be delete and recreate the SQS queue, which obviously wipes out all the healthy pending orders.
Which would be a disaster.
Yeah, huge disaster. The architectural best practice is to configure a dead letter queue on the primary SQS queue and set a redrive policy with a max receives count of 3 or 5.
Once that incorrectly formatted record hits that threshold, SQS evicts it to the DLQ, clearing the blockage for the valid records. Walking through these scenarios and reading the prompts for keywords like reliable or nested JSON or continually retries, that is how you translate theoretical knowledge into a passing score.
We have covered incredible ground today. Just to recap our journey through the AWS serverless architecture, we started with Lambda, exploring how triggers bring code to life and why concurrency limits act as necessary blast shields for downstream legacy systems.
Yep.
We decoded the decoupling intermediaries, identifying SQS as the durable buffer, SNS as the high-throughput fan-out, and EventBridge as the intelligent cross-account router. We tackled operational resilience by using dead-letter queues to isolate those nasty poison pill messages. And finally, we proved how those concepts apply directly to the SAA CO3 exam scenarios.
And honestly, whether you are preparing to sit for that certification tomorrow, or you simply want to grasp how modern software engineers prevent catastrophic failures at scale,
Yeah,
the event machine mindset is an invaluable framework.
it really is.
It forces you to stop viewing applications as monolithic blocks of code and start architecting them as living ecosystems of independent, resilient, reacting components.
It is a profound shift in how we build on the cloud. But before we wrap up, I want to leave you with one final lingering question to ponder. We've spent this deep dive exploring how decoupling everything, putting queues and buses between every single microservice, absorbs shocks and isolates failures. But consider the operational overhead. If a single user action requires a payload to bounce through an API gateway, into an SQS queue, through a Lambda, out to an EventBridge bus, and into 3 different downstream databases, observability just becomes a nightmare.
Absolutely.
So at what point does the sheer complexity of tracing millions of asynchronous events and the human error involved in configuring all those independent moving parts become a greater risk to the system than the monolithic problems decoupling was supposed to solve?
That is the ultimate architectural balancing act. Resilience always comes at the cost of complexity.
Next time you look at that sprawling, perfectly automated factory, just remember, every single conveyor belt is another moving part that someone has to monitor, maintain, and eventually troubleshoot. Thanks for joining us, and we'll catch you on the next deep dive.